Okay, so picking up part 2 of the 4-2 notes here. And most of this part's going to just entail some examples, so follow along as I go through these. Some of them won't be too bad, but there are a few that are a little bit trickier. So again, just kind of follow along, and obviously if you have any questions, come let me know. But example 2 here hopefully is pretty easy. So a spring-loaded gun launches a 10 gram. It is a gram, so I'm going to convert that to kilograms, right? That'd be 0.01 kilograms. Plastic ball, the spring with a constant of 10 newtons per meter. It's compressed 10 centimeters, so I'm also going to go ahead and convert that distance, that delta x, to 0.10 meters. When the trigger is pulled, the spring is released and shoots the ball back out. What is the ball's speed as it leaves the barrel? And so we're assuming in this one that it's just being held horizontally here. So you've got the spring, it's been compressed, the ball is in it, right? So it's compressed a distance of 0.1 meters. As you then release the ball, we know that the ball is going to be fired outward because we're going to transfer our spring potential energy to kinetic energy, right? So initially, as it's compressed, we have spring potential energy. As it gets released, that energy converts to kinetic. And that's obviously the key relationship then for part A. So again, hopefully part A, nothing too tricky here. It's just taking advantage of that equation, that relationship. So the elastic potential energy stored in the spring converts to it equals the kinetic energy as the ball leaves the spring, right? So then just 1/2 kx squared equals 1/2 mv squared. Obviously, if I look at this equation, yes, the 1/2s can cancel out. I've got the spring constant of 10. I know that it's been compressed 0.1, which I'm squaring. And then over here, I know the mass of the ball is 0.01, and then my velocity is what I'm looking for. So at this point, a pretty easy setup, right? Solving it from here, you get that v squared equals 10. So when I solve this out, I get v squared equals 10, which then means v equals the square root of 10. So v equals about 3.16 meters per second. Right, so v equals 3.16 meters per second. So that's how fast the ball goes as it leaves the spring. So part A, nothing too tricky. Part B, what would the energy charts look like for this ball's motion? So let's just kind of make a couple of those. I know that's a very open-ended question, but once again, I do want you to be comfortable making these energy charts as you need to. So initially, right, the initial energy chart here, when it's compressed all the way, all of my energy would be elastic or spring potential, right? My kinetic energy would be 0. So I don't have any kinetic energy, but I do have spring potential energy. And in fact, we could find that number, and I think I did go ahead and do that for this one. So if I wanted to find that initial elastic potential energy, it's just 1/2 the constant of 10 and then my 0.1 squared. So obviously when I calculate all of that, I end up with a potential energy of 0.05 joules of energy. Right, so that just gives me a numerical reference here then on my vertical axis, right? So I'm just going to mark up here as 0.05. That's how many joules of energy I start with, and to begin with, it's all spring potential, right? So that bar goes all the way up, and again, I don't have any kinetic energy. So there's my first graph for part B. My second graph would really just be the opposite. As the ball is leaving the spring, right? Once the spring has completely decompressed, once it's not compressed anymore, then there's no longer any spring potential energy. So this is now 0, and all of the energy is converted to kinetic energy, right? So I now have only kinetic energy extending upward, right? It is still the same amount of kinetic energy because no energy is lost, assuming there's no friction. Anyway, I know I went through that pretty quickly, but hopefully part B isn't a terrible part to get through. So question 2, hopefully mostly review here for us, but if you do have any questions, come find me. Okay, so while example 2 is hopefully pretty easy, this example here, example 3, probably a little bit trickier. So this is one that I do want to make sure you guys take your time on and definitely follow through as I go through this. Like I said, it's going to be a slightly more challenging example, and this is also the style of question that the AP test really likes because they have you kind of interpret a graph and then find some information from that. So anyway, let's get to this question. Your lab assignment for the week is to devise a method to determine the spring constant of a spring. You happen to notice that there's several objects lying around. You decide to measure how high the compressed spring will launch each of those blocks. You quickly realize that to keep one value the same, you're going to compress it each time to be 4 centimeters compressed. Then you measure the height from where you place the object of the compressed spring there, and then you measure that height of how high it went. what value will you report for your spring constant? So obviously, first and foremost, it's important we realize we're looking for K, right? So that's the value that I'm looking for. So the notion here is you've got a spring, you've got a vertical spring, and then you just start placing random objects on it, compressing them the same distance of 4 centimeters, and then launching them upward, right? So that's what's going on here, right? I'm just taking those, compressing them, and I'm launching them up, right? So what's happening then, right? What's the actual relationship going on? Well, when it's compressed, it's storing potential energy due to the spring, right? That potential energy converts to some kinetic on the way up, yes, but by the time that it reaches the highest point, where has all of that potential spring energy gone? Well, once the object is launched up and reaches its highest point, all of that spring potential energy is now gravitational potential energy, right? So I can really cut out the middleman. I don't need the kinetic energy. Really, the relationship that I want to be exploring here is the spring potential energy equals the final gravitational energy, right? So then if I start to break this up and I start to look at what measurements do I and don't I know, well, this is 1/2 kx squared, which is good because that may give me a route then to find k. This over here is mass times gravity times height, and obviously if I look at the table, I know the mass and I know the height, right? So as I start to look through this equation, it does definitely look good because it gives me a route to solve for k. Now the tricky thing though is with an experiment like this, you don't just want to use one set of data. I don't just want to take this mass and this height and plug them in and then see what I get, because you're going to get various different values for k. So instead what we want to do is we want to graph this, and we want to graph it in such a way that the slope can help me find k. So I'm going to take this relationship, right? I've got my 1/2 kx squared equals mgh. And my goal is to make this look like a linear function, right? So I want to do something with this such that it's kind of like a linear function. And obviously linear function equals, or in the form of y equals mx plus b, right? So I want to make this somehow kind of fit the mold of my y equals mx plus b. Well, the two variables that I have here, right? One of these would be my independent and one of these would be my dependent variables, right? So I'm going to go ahead and say then that the mass maybe is my y and the height here is my x, or vice versa. It really doesn't matter, but I'm going to go ahead and define those as such, right? So is there any way that I could make an equation out of this using mass and height? Well, if I looked at this, not quite, but what I can do, let's just presume that my mass is going to be my y variable, and let's not worry about the x just yet, right? So instead, let's assume that my y value is my mass. Let's take this equation, right? So I'm going to start with this equation right here, and I'm going to solve it for my mass because I want it to look like y equals mx plus b. Right, so I'm going to solve this equation. I'm going to get the mass by itself. So all that entails, right, is dividing both sides by g and h. Right, so I'm dividing both sides by g and h. So I end up getting mass. I'm just converting that and moving that over here. And then equals k times x squared all over 2gh. Well, if I start to look through here, again, my goal is to make this look like y equals mx plus b. My m is acting as my y, so that's okay. What's acting as my x? Well, let's start to identify what are constants, right? The k is a constant. The x I kept the same, so the x is actually a constant value in this particular problem. Both the 2 and the g are also constants. So all 4 of these measurements right here, these are all constant values. And so really what I can do with that then is I can make all 4 of those together represent my slope. So then what does that leave for my x value? Well, that leaves on bottom I've got an h, and then on top I would just throw a 1. So what this means is my x value is essentially 1 over h. And this is not the only way you could do this equation. You could also solve it for h and then find out what your x value would be in terms of m. You could do the exact same thing. But basically what I'm saying here is I've solved my equation for m. M equals kx squared over 2g, and then I'm going to go ahead and multiply that off to the side by 1 over h. The reason I'm doing that, the reason I'm breaking that up, h is one of my variables, and so this is acting as my x value, this is acting as my m value, and then my m over here, my mass, is acting as my y value. If I think of these values as such, then I've got a linear equation. So then how do I use this information to actually help me solve for k? Well, the idea is I know k is part of the slope, right? I know k is part of my slope. So I'm going to take this information, I'm going to take this equation, and I'm going to graph it in terms of my y value, which I'm using what to represent my y value, Well, I'm using my mass, right? So my y value is my mass, and what's representing my x value? Well, it's 1 over the height, right? So it's 1 over h. So I'm going to plot my mass along the vertical axis. I'm going to plot 1 over h along the horizontal axis, and then my slope would represent this entire value right here. So when I do that, well, obviously to plot these points, I need to know my mass and 1 over h. They gave me my mass. Keep in mind, I do want to convert that to kilograms. So I'm going to go ahead and make this 0.05, 0.1, 0.15, and then 0.2. Right, so I've gone ahead and converted those to kilograms. And then I actually don't want my height, I want 1 over my height. So I'm just going to take each of these numbers and do 1 divided by that number. Right, so 1 divided by 2.07 ends up being about 0.48. 1 divided by 1.11 ends up being about 0.90. 1 divided by 0.65 ends up being 1.54. And 1 divided by 0.51 ends up being 1.96. So I'm actually going to take these values and plot those. Right? So in other words, I'm going to go over about half, right, 0.48, and then up 0.05. Right? So just looking at my scale now, I'm going to go up by maybe 0.5s here. So 0.5, 1, 1.5, and 2. And then here I'm just going to go up by 0.05s, right? I'm just plotting the points that I now have. And obviously the vertical axis is nice because those masses were nice and uniformly increasing. So it's easier to scale that one. But anyway, I know obviously if it was 0, it would start at 0, 0. When the first value there, again, when the mass was 0.05, it went up to a height, or it went to 1 over the height of 0.48. When the mass was 0.10, it was almost at 1, so it was about 0.9. And so on and so forth, right? When it was 0.15, it was close to 1.54, so it was somewhere over here. And then my 0.2 ended up being pretty close to 2. It was about 1.96. So obviously this doesn't end up being a perfectly straight line, and my graph, of course, being my graph, is worse, right, than that. But what we would do with this is then we would draw on our line of best fit. So I've got my line of best fit now. And then from that line of best fit, I would choose any 2 points that fall on that line. So maybe I choose this point and this point, and I can use those 2 points to then find my slope. Right? So if I do choose these 2 points, I would find my slope. So my slope would be, of course, my rise over run. So it would be 0.20 minus 0.05 divided by my run, which I'm using these 2 points. So it would be 1.96 minus 0.48. So I'd find my slope, and then I would set my slope equal to the entire mess, kx squared all over 2g. But keep in mind, I know that g is 9.8, and I know that my x is 0.04 because it's 4 centimeters, right? So 0.04, which I'm then squaring. Okay, so at this point, once I realize that the slope represents this entire part of my equation, then I can solve for k. And so that's all we have to do then is just go through. We have to solve for k. I will leave that to you guys to go ahead and calculate it. But I end up getting that k is about 1,230 newtons per meter. Right, so I've rounded that off a little bit there, but k ends up being about 1,230 newtons per meter. So again, this question definitely trickier, right? You have to take your information, start with the relationship, do what we call linearizing the curve, which means take this function and represent it as a linear equation. Think about what your output would be, think about what your input would be, right? So my input was 1 over h, my output was m, and then solving for the slope, I find out that this whole thing is my slope, then I can use that to help me find k. So again, you do not want to just use one set of data there. You actually want to graph the data, find 2 points from the line, use the slope, and then use the slope to help you find k. So definitely make sure you're comfortable working through this problem. Like I said, I know it's always tough to do these over the internet here, so if you do have questions on this, please come find me so I can help you out. But we'll stop the second part of the video on this question since that took a little while to get through.